these two parts there are sort of, so I really like the questions. The answers that we have are kind of, you know, they're something, but they leave a lot to be desired. So, okay, so what setting are we in? So, okay, so suppose we give an n independent draws from some d-dimensional distribution. So throughout, maybe think of this distribution as being a Gaussian. So one natural question is, well, how large must our number of samples be, say, in comparison to d, to actually understand, say, the structure of the distribution? So one notion of structure is the eigenvalues of the covariance matrix. Okay, so right, so the eigenvalues of the covariance, they basically indicate whether there's you know, some low-dimensional representation of the distribution, right? So, you know, if you have a bunch of 0 eigenvalues, it means that your distribution lies in some lower dimensional subspace and so on, right? So, yeah, so again, as I said kind of at the very beginning, if you have too little structure to actually find this, sorry, if you have too little data to actually find the structure, so say, you know that the principal components are going to be misleading. Can you still say whether or not there is structure? Okay, so you can't tell me what the eigenvectors are of the covariance, but maybe you can tell me the eigenvalues. Okay, you can't tell me what low-dimensional subspace the data lies in, but maybe you can tell me that it does lie in some low-dimensional subspace. So, okay, so this is kind of the empirical approach. So say we take, we have this data matrix Y, and think of it as, say, it's 1,000 independent draws from some 1,000-dimensional Gaussian. And suppose we plot the histogram of the eigenvalues of the empirical covariance. Okay, so we compute the singular value decomposition of Y transpose Y, and we see something like this. So this means that there are some directions with biggish variance, most directions the smallest variance. And suppose someone comes and asks you, well, what do you think the true covariance is of the distribution from which we drew this? So what would we guess? We all have good priors on this, so. Okay, so someone say something. It doesn't matter. Yeah. Okay. This is a semicircle. Yeah. So this is like actually a semicircle and somewhat. Yeah. So yeah. So. Okay. Actually, so yeah. So I'll just go back to the motivation once more, or not the motivation, but the the problem. So. Okay, so we're going to be given n independent samples from some d-dimensional distribution. Okay, and throughout you can kind of think of the distribution as just being a Gaussian. See, so d-dimensional Gaussian, n independent draws, and our goal is going to be to learn the spectrum. So the eigenvalues of the covariance matrix. That's what we want to learn, right? And these eigenvalues, they tell you sort of to what extent your distribution lies in a lower dimensional subspace and so on, right? Yeah, to what extent there's structure in the distribution. Okay, so in the regime where you have too little data to learn the eigenvectors of the covariance, so you have too little data to accurately learn the principal components, can you still learn the eigenvalues of the covariance? Okay, so you can't learn the eigenvectors, maybe you can still learn the eigenvalues, which tell you sort of how much structure there is, even though they don't tell you what the structure is. They don't tell you, the directions of the structure, but they tell you that there is some low-dimensional structure. Okay, so we had this example. So that we have this data matrix Y. It's 1,000 independent draws from some 1,000-dimensional Gaussian. We're going to try to guess what the covariance is, what the eigenvalues of the covariance are. These are the eigenvalues of the empirical covariance. It's just like the SVD of Y transpose Y. Okay, and yeah, what distribution did this come from? As you might have guessed, this was obtained by taking samples just from an identity covariance matrix. So the true distribution, none of the directions are special, But because we only took d samples from a d-dimensional thing, some of the directions look like they're good, some of the eigenvalues are big, and a lot of the directions look small. Okay, but that's just from the sampling noise. Okay, so basically, as in the first part of the talk, the question is, well, say I just show you this. Is there a kind of principled way of going back and arguing that and concluding that yes, actually, I think maybe all of the eigenvalues are the same? Okay, is there a way of, given the empirical eigenvalues of the covariance, can we denoise it and conclude actually all the directions are basically the same? Okay, are we okay with? Okay, so right, so slightly more formally. So we're given an n by d data matrix Y. So d is the dimension, n is the number of samples. And we're assuming that our data is drawn kind of from this product. So X is an n by d matrix, independent entries, and each entry say is drawn from distribution with mean 0, variance 1, and say bounded fourth moment. This matrix S, this is some arbitrary d by d real valued matrix. Okay, so what's so what's going on? So right, so we have our data matrix Y, which is n by d. So in the case, say you want n independent samples from a Gaussian of covariance sigma. Well, X is just all these entries are independent Gaussians. S is going to then be like the square root of sigma, right? So if you want Y to correspond to Gaussian, then S is going to be the square root of your covariance, and this will be like IID Gaussians. The entries of X will be independent. Okay, so I'm just saying this model captures a case where we're getting independent samples from a Gaussian. In the case where X is not independent Gaussians, then you get other more general distributions. Okay, so you can represent samples drawn from say rotated hypercubes and so on can also be represented like this. Okay, so are we okay with the setting? So we're given this data matrix Y, and the goal is to accurately recover the population spectrum. So namely, we want to recover the eigenvalues of S transpose S. Okay, right. So again, in the Gaussian case, this is the covariance, and we're just getting the eigenvalues of the covariance. Okay, so just how can you think? How do you think about this? So given this list of eigenvalues of the covariance, you can also imagine this as a distribution. You can think of it as so it's known as a spectral distribution, and just think of it as a distribution of d point masses located at each of the eigenvalues. Okay, right. So if these are the eigenvalues, just think of this distribution with these point masses. And recovering this set of eigenvalues, or this sorted list of eigenvalues, in total variation distance is equivalent to recovering this distribution in earth mover distance. Okay, so if I have a sorted vector, and I want to recover the sorted vector in L1 distance, it's the same as thinking of this as a distribution and recovering it in terms of earth mover distance, or Wasserstein distance. And again, Wasserstein distance between distributions, you have two distributions. The earth mover distance is just the cost of the cheapest scheme of moving the mass in one distribution to make the other distribution, where the cost of moving probability mass, P from X to Y is P times absolute value of X minus Y. So for each unit of probability mass that you move distance d, you pay d. Okay, so learning this sorted list in L1 distance is the same as trying to recover this distribution, the spectral distribution in earth mover Wasserstein distance. Okay. Okay, so what's known about this problem? So there's this Marchenko-Pasteur law. I'm not pronouncing it with the nice French pronunciation, but which basically says, so when you have large number of samples n and large dimension d, the empirical spectral distribution, so the eigenvalues of the empirical covariance, is well approximated by some function of the population, of the true population spectral distribution, assuming that the ratio of the number of samples and the dimension is constant. Okay, so in other words, going back to our example, the Marchenko-Pasteur law basically says, look, like this shape here is the same shape you would see if I replaced 1,000 and 1,000 by 10,000 and 10,000, as long as the true covariance was still the identity. Okay, so basically says that if you had seen lots of this, you should have been able to see this shape and say, aha, I understand that this was taken from an identity covariance Gaussian. That's all the Marchenko-Pasteur law says. Okay, and crucially, it sort of it requires that the ratio of the number of samples and the dimension be constant in order to really work. So given this, the kind of natural approach to to recovering the true population spectrum is to try to invert this Marchenko-Pasteur law. So this was kind of some work of Gregory in 2008. So basically saying, look, the Marchenko-Pasteur law says, given a true spectrum this, the empirical spectrum will look like that. And you can imagine going the opposite way of trying to invert this. And it sort of works, but crucially, it's kind of limited to this regime where the ratio of the dimension number of samples is constant. Okay, so in the subconstant regime, it kind of can't really say anything, and it actually starts to fall apart because you don't have this kind of Marchenko-Pasteur law really holding. Okay, so we want to kind of do something in the sublinear sample regime, and so the game plan basically has two parts. So it's going to be a method of moments. So the first part, we're going to argue that we can accurately recover the low order moments of the true population spectral distribution. So like the second moment is like the sum of the squares of the eigenvalues. The third moment is the sum of the cubes of the eigenvalues. And the second part is just solving this moment inverse problem. So okay, you tell me what the sum of the squares of the eigenvalues are, sum of the cubes, sum of the fourth powers. I'll give you this spectral distribution. I'll give you this set of eigenvalues. Okay, so the theorem shows that there's an efficient algorithm that approximates the kth moment, the sum of the kth powers of the eigenvalues, with multiplicative error, this thing, some function of k, and then essentially the dimension to the k over 2 minus 1 over the number of samples to the k over 2. And the fact that you have this minus 1 here is kind of what gets you this sublinear. So if you want to estimate, the third moment, well, this is d to the, 3 halves minus 1. So the dimension to the 1/2 over n to the 3 halves, which is very subconstant. So this is saying that, you're doing a really good job estimating the third moment in this kind of sublinear setting, say. Okay. Don't worry too much about this exact expression. And this is actually optimal. So you, information theoretically, you can't estimate these moments better than this. Okay, and the second part just says, look, if I have two distributions whose first k moments are similar, then their Earth mover Wasserstein distance is similar. Okay, so you match k moments, you get error roughly 1 over k, and this is robust. This just follows from kind of the fact that you can represent any Lipschitz function to error 1 over k with a degree k polynomial. Let's not worry about this. Okay, so all I'm arguing is, look, if we can do good moment estimation, then we can actually recover our eigenvalues. Okay, this is formally what the theorem says. The only things I want to point out, so Yeah, so we're in this model where our data is some random matrix X times some arbitrary matrix S, where the entries are independent but have bounded fourth moment. And okay, so this basically says something sublinear is possible. Maybe let's not parse this. So it comes just from applying these two facts. This one is tight. This one is tight. When you put them together, I don't know if it's tight. Okay? So I don't have a matching lower bound for this, but let's skip that. Okay, so how do we do this? So how do we? Sorry? In what sense are we recovering these moments? Or yeah, so with high probability, we're recovering the moments accurately. And then given that we have accurate estimates of the moments, then we have an accurate L1 distance on the return vector of eigenvalues. Okay, so how do we get these, how do we estimate the moments? Okay, so consider the following definition, which, so I think it's been around for a while, but is also used in this paper of Lee, Nguyen, and Woodruff. So consider a k-cycle, which is just a sequence of k distinct numbers between 1 and n. And given an n by n matrix A and a k-cycle sigma, you can associate the following product to this k-cycle. So it's a product from I equals 1 to k of the entry, the first element of your cycle, comma the second entry, times the matrix with the second entry, comma the third entry, times the matrixing with the third entry, comma the fourth entry, blah, 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 to the matrix with the kth entry, and then the first entry. So it's this kind of cycle where you're working your way around this kind of cycle in your matrix. If you look at the product of this, there's the following observation. So you take our data matrix, you look at the data times the transpose of it. For any k-cycle, the expected value of this is exactly the kth moment. Okay, so the claim is this is actually an unbiased estimate of this kth moment of the eigenvalues. Okay, this isn't too hard to see, but it's not a good use of time. Okay, if instead of k-cycles being k distinct numbers, it's just some list of k things, this isn't true. But what it corresponds to is the expectation for any non-distinct kind of list of k things. This is just the kth moment of the empirical eigenvalues. So going from this, adding this distinct thing gets you an unbiased estimate. Okay, we'll come back to this in a sec. Okay, so how do we turn this into a good estimator? So the naive hope is we can just sum, we can compute this product and sum over all the different k-cycles. And the resulting estimator, because it's a sum of unbiased things, it'll be unbiased. Because we're adding this up over all these different k-cycles, maybe the variance will be small because we're adding it up over lots of k-cycles. Okay, so there are kind of two issues. The first thing is the sum over all these k-cycles can't be computed efficiently. So if you have, say, a matrix corresponding to a graph, the sum over k-cycles starts to turn into some, looks like you're counting something that you shouldn't be able to count. And you can show this actually NP hard when k is large. So that's kind of a problem. If you got rid of the fact that your k-cycle, you need k distinct elements, and you just were to sum over these products of not necessarily distinct things, then you can do this efficiently. But then it's biased, and this is just the empirical kth moment, okay, which we know is not good. Okay, and the second kind of issue is certainly in the non-Gaussian case, it's hard to show this kind of variance bounds for the sum over all these k-cycles. Okay. Okay, so the one rock that kind of hits both of these birds is if you only consider increasing k-cycles, so where like it's k distinct numbers that are increasing, and you just sum over all these, well, you can compute them efficiently in time basically matrix multiplication time, And showing this concentration is actually a bit easier. Some of the dependencies disappear. Okay, so what does the algorithm do? Well, you have your data matrix Y. This n by n matrix A is just Y times Y transpose. You zero out everything below the diagonal. And then you output the trace of this thing, this G to some power, k minus 1 times A, over some normalizing constant. Okay, so it's very easy. Estimating the kth moment is very easy. It's just this matrix products. If you were to just compute the empirical kth moment, you would just output this kind of trace of A to the k. And this is like very biased. So we're doing something similar, but we kind of do this slightly clever thing by zeroing out the diagonal, and this kind of solves our problems for us. Okay. But anyway, so it's no harder than doing the empirical thing, but you get a good unbiased thing. Okay, so how well does this approach actually work in practice? It actually works pretty well. Can people see this? Okay, maybe let's look at this plot. So what is this? These are plots and lots of different trials of recovering the following true eigenvalues. So this is a true spike setting. So this is a CDF of the eigenvalues. So half of the eigenvalues are at 1, half of the eigenvalues are at 2. This blue line is the truth. The red lines are kind of what we recover. And the faint blue line is the empirical spectrum. So this is lots of different settings of parameters. So this is so each column keeps the ratio of the samples to the dimension constant. So you can think of the Marchenko-Pastor law as saying that this light blue line here is going to kind of converge. For every column, this light blue line should converge, which it looks like it does. And we're doing a pretty good job of recovering things, even in a slightly, even when kind of the number of samples is like a little lower than the dimension. And for other, it actually works pretty nicely. Here the spectrum is kind of, the eigenvalues are uniformly distributed. This blue line, we're doing a decent job. Toeplitz matrices, anyway. Okay, this is all I wanted to say about this spectrum recovery. So, we can do, we can do things in the sublinear regime. There's still quite a lot of open questions, so we don't have matching lower bounds for the spectrum recovery, but I think our algorithm should kind of be information theoretically optimal. And it seems to actually work pretty well in practice. One other direction to go is, say you don't just want to learn the eigenvalues. You actually want to accurately learn the covariance itself. So one natural approach is, well, take the empirical eigenvectors of the covariance, take those directions, but rather than multiplying them by the empirical eigenvalues, you should multiply them by the corrected eigenvalues. So this is kind of reminiscent of the first part of the talk, where we would correct the unlabeled probabilities and then add the labels. Here it's like saying we're correcting the eigenvalues, and now we can add back the eigenvectors and get a better approximation for the covariance. So I'm not exactly sure what guarantees one gets for this, but I think it's probably going to be better than these usual standard approaches of doing some kind of pretty arbitrary shrinkage to the eigenvalues before multiplying them back in. Anyway, I don't know if any of you guys follow that literature.
Yeah, no, just
oh,
yeah. I mean, you cannot recover the eigenvalues well by doing the empirical. Why should you recover well the eigenvalues?
No, this is completely true. But think of it in the regime where, say you have quite a lot of samples, and the eigenvalues are pretty accurate. The empirical eigenvalues are pretty accurate, and the empirical eigenvectors are pretty accurate. Then if you can get even more accurate estimates of eigenvalues, you might as well use them. Okay?
Somehow it's like the eigenvalues are more sensitive?
They're not more sensitive, but somehow you can do more with them. Or if you can correct them, you might as well. Right? And again, going back to that example at the very beginning, where sure, the eigenvectors are all garbage, but the covariance is just the identity. So, if you recover the fact that all the eigenvalues are the same, it doesn't even matter that your eigenvectors were arbitrary. Right? So you can think of it that way, that sometimes after this rescaling, you'll be perfect even when the vectors are garbage. Okay. Okay, the last part of the talk. So if you've not been following, you can join back. Okay, so the setting we are in. So we're given this matrix of probabilities, Pij. We're going to get samples as follows. So each draw consists of some ij pair, and we pick I comma j with probability Pij. And we get this matrix of empirical counts. Okay? No, so if we take n draws, then the sum of all these entries will be n. Okay. Actually, sorry, so here n denotes maybe this, assume maybe this matrix is n by n, and then say we draw t independent draws, so the sum of these entries will be t. Okay. So why might we care about the setting? Well, okay, so here are some practical settings. So suppose that the columns of this matrix are indexed by customers, the rows are indexed by products. Pij represents the probability that the next person on Amazon, or the next purchase from Amazon, will be customer j purchasing product I. Okay? And these empirical counts, this is the history of who's bought what. Right? So obviously this matrix is very sparse. Yes? Okay, a slightly different motivation setting for this is have all this work on word embeddings. So how many people are kind of familiar with word embeddings? Okay, so this has kind of been this idea that's been maybe the most exciting thing that the natural language processing community has been going on about for the last maybe two years or so. And the idea is basically, can we compute some way of mapping words to vectors such that the geometry of the vectors correspond to the semantics of the words? Okay? You can think of it as just asking, is there a good featurization of words? Okay? And currently what's, one of the approaches that's done now is you get a big matrix where the ijth entry, so where the columns are indexed by words, the rows are indexed by words, and the ijth entry is the number of times the ith word and the jth word have co-occurred, next to each other or in the same sentence based on some big corpus. So you go through all of Wikipedia, you make the co-occurrence matrix, and then what do? So in practice, you do something slightly funny. You take the element-wise square roots or element-wise logarithms, and then you compute the SVD of this. And if you want 100-dimensional word vectors, you approximate this by the rank 100 matrix, okay, where this is 100. And now the 100-dimensional word vector corresponding to the ith word is just the column here, corresponding to the ith column. Okay, and the rhetoric, which is almost true, is that this actually has nice properties. So the usual rhetoric is take the vector corresponding to the word king, subtract the vector corresponding to the word queen, and this vector is actually almost the same vector as the difference between the vectors corresponding to it's almost the same vector as that corresponding to the difference between uncle and aunt and boy and girl. Okay, so in this sense, the geometry represents kind of the semantic, the boy version, girl version of a word. Okay, okay, so you can imagine, well, there is some matrix of probabilities representing, Pij is the true probability that the ith word and the jth word co-occur in a natural English sentence. We have this empirical counts based on Wikipedia. And well, we don't care about this object. We want to understand this object. Okay? And the question is, given this object, what can we say about this object? Okay, so given this object, and say this object's rather sparse, we have relatively few samples from this. What can we say about this thing? So there are lots of questions. You can ask, well, what structural properties of this can be leveraged to help you recover this from this? Yeah.
So what exactly is the problem? Is the problem that you don't have enough pairs, or that they're biased, or what do you assume about?
Yeah. So the following question is like one. So you can ask lots of questions. One question is just say you have an n by n matrix, and I give you much less than n squared samples. Okay. So the sum of these entries is much less than n squared. So most of these entries are 0, right? In this regime, say someone wants to approximate, say I want the best rank 100 approximation to this matrix. How do I do that? Is the best rank 100 approximation to this matrix the same as the best approximate? No. And if I want the best rank 100 approximation to this matrix, maybe I should do something more clever than returning the best rank 100 approximation to this matrix. Yeah.
So the point is that the empirical distribution is only good when the sample size scales at least linearly with the size of the domain. The domain here is n squared. So if you take n squared samples, the empirical is going to work. Information theoretically, we know that in this setting, n samples are enough. So the question is if you can actually do n samples, n polynomial time. Right?
Yeah. So I guess this is. Okay, we'll see. Wait one more slide, and then if there's any uncertainty in what we're doing, ask. Yeah. So okay. So here's a very modest starting place. Assume that the true matrix has rank 2, and it has like 2 non-negative factors. Okay. How do you recover this matrix from this empirical thing? Okay, so this generalizes a few natural problems. So one is this community detection problem. So the standard, community detection problem, like the stochastic block model, is as follows. So, the rows and columns are indexed by people, and each person is a member of one of 2 groups. Okay, so say this is group 1, this is group 2. This is group 1, 2. Okay? And the stochastic block model says that the probability that 2 people in the same group are friends is p. So all these entries are p. Maybe there are zeros on the diagonal if you're not, but don't worry about that. These entries are all p, since people in the same group. And the probability that someone in group A is friends with someone in group B is some other value, say q, and assume that q is less than p. Okay? So this is kind of the model of the world. And we're going to sample the adjacency matrix of a graph according to these probabilities. Okay? So this is kind of the true structure of the world. And then we sample the adjacency matrix of a graph according to these things. So we see some friendships. Okay? Everything else is 0. And then, a question is, given this, can you infer, the group structure? Okay, so for each of these individuals, based on this graph, can I say, okay, these guys are in one set, these guys are in another set? Okay, and even though this matrix is size n squared, there are n individuals. The question is, how many edges do you need? Like, is it okay if you only have a linear number of friendships, say, assuming p and q are, differ by a constant factor or something? Okay, and there's been a lot of work from the kind of probability community on community detection. And yes, even in the linear regime, where you only have like order n edges in this graph, you can still infer the community structure. And this is true, this okay? Okay, right, so this matrix has rank 2. We have this empirical thing. The best rank 2 approximation of the empirical thing is not what you want to recover the structure. Okay. Okay, so like the learning community has also been looking at kind of some tasks which can be mapped into this matrix recovery problem. So there's this problem of like learning topic models. How many people are familiar with this? A few people? Okay, so so this problem, like there are 2 topics. There's topic P and topic Q. Each topic think of as a distribution over words. Okay? And there's also some probability of these 2 topics. And a pair of words sampled according to this topic model. First, you flip a coin with probability, W. You pick some words from topic 1, from topic P. And with probability 1 minus W, you pick some independent words from topic Q. Okay? This is kind of the topic model setting. Okay, and you can think of it as like one topic is like baseball, one topic is politics. Maybe if you pick a random place in Wikipedia, all the words will be sort of sampled from either the, sports or from politics and so on. Okay, it's a crude model. So again, in this setting, if you look at the word co-occurrence matrix, it corresponds to W times this matrix, W times the distribution, the vector corresponding to the distribution, times its transpose, plus a thing for the other distribution. And this true matrix has rank 2. And the observed word co-occurrences correspond to the sampled matrix. And the question is, how can you go back and learn this matrix, which is kind of equivalent to learning the topics? Okay. Also, the problem of learning a hidden Markov model with, say, 2 hidden states and observations drawn from distributions over n things can also be viewed as corresponding to this learning this rank 2 matrix. Okay. Okay. Okay, so what can we say about this setting? So again, the things that we can say are all kind of rather modest, but the general questions I think are definitely worth looking at. And at a high level, the kind of people in probability theory have been looking at this stochastic block models, which is a very special case of these more general problems. And these more general problems seem extremely relevant, right? So this word vector stuff, lots of people are using it. This products and customers, how do you run a recommendation system? Right? You have products, customers. You want to figure out, what are you going to buy next so that I can advertise this to you on your stupid banner thing, right? This is the way the internet works. So, how do you do this? Generally, you have this you have some data. You usually try to find a low rank approximation to your customer product matrix, and then use this to suggest products. Okay. But what you would like is a low rank approximation to the true matrix, not just a low rank approximation to your noisy data, right? So anyway, so the question is basically how can you do something better than just outputting, say, a low rank approximation to the data if what you want is a low rank approximation to the truth. Okay, so what can we do? So given an unknown n by n rank 2 matrix, and an observed count matrix derived from a linear number of samples, or say order n over epsilon squared, you can efficiently recover the true matrix in L1 distance efficiently. Okay, so that's kind of the theorem. Again, so L1 distance is in this, it's stronger than spectral or kind of L2 distances. So, you can learn topic models, you can learn HMMs, and so on. Okay, also, we have like very strong lower bounds in the following sense. So, never mind for this learning task. Say all you want to do is distinguish. I give you this observed matrix, and I ask you, is the thing from which it was sampled, is this guy, is it rank 1 or is it rank 2? Okay, I don't want you to partition it, I don't want you to learn it, I just want you to tell me, is this thing rank 1 or rank 2? Okay? So this requires order n samples. There's no, you can't get away with a sublinear number. Okay? Or, yeah. Okay, if this is an n by n matrix, you need order n samples to do this task. Okay? And okay, and this is actually true even in this hidden Markov model setting. So, okay, so this will kind of be a picture of, well, okay. So, so you're given like independent samples from some distribution over n things. So, you know, learning, how can you learn a distribution over n things? Sorry. Yeah, how many samples do you need to learn a distribution over n things? You know, well, you need kind of order n samples. Okay, and you know, if you have samples drawn from this, say, a 2 hidden state Markov model, where the observations are drawn from distributions over n things, sure, given order n samples, you can learn it. That's, you know, that's what we showed. But say you don't want to actually learn the thing, you just want to estimate some properties. So, you know, given independent draws from some distribution over n things, yeah, given a sublinear number of samples and over log n, you can estimate, say, the entropy of the distribution. Say you want to distinguish, you want to just test, is your distribution the uniform distribution? You can do this with square root of n samples. Okay. So basically, our lower bounds show that, well, you know, all you need is a bit of dependence. So say I have independent draws from, sorry, I have a sequence of observations from a hidden Markov model with 2 hidden states. So if you want to estimate the entropy rate or something of this Markov model, or you want to estimate, or you just want to decide, is there actually a 2 hidden state Markov model, or is it just independent draws? This you need order n samples. So somehow, even when you just have this little, you know, 2 hidden states rather than just kind of 1, suddenly like sublinear property testing and estimation becomes impossible. Okay, that's one interpretation of this. How much longer should I go for? 5 minutes? Okay.
Up to 10's
okay. Well, okay. So how many people would rather hear a tiny bit about the algorithm, and how many people would rather hear a tiny bit about the lower bounds? So algorithm. Okay. Lower bounds. Oh. Okay. The third option is we hear Elias. Okay, sorry. Okay, so maybe I'll give a little intuition behind the algorithm, and then we'll see. So okay, so again, so we have this rank 2 matrix P, empirical counts P hat. So what's wrong with just the naive algorithm of returning? So again, we want, you know, what's wrong with just taking the best rank 2 approximation of this guy? Well, you know, if this thing is just the uniform distribution over this whole thing, the rank 1 matrix where all the entries are 1 over n squared, if we're given n samples, you have this empirical matrix, what happens? Well, basically with high probability, there exists some row or column that has like, you know, on the order of log n over log n 1s. Okay, so this is like saying you have a random graph. Each edge exists with probably 1 over n. With high probability, you have, you know, a few nodes whose degree is kind of super constant, whose degree might be as high as like log n over log n. And basically, these heavy nodes, these heavy rows and columns, are going to throw off the spectral approach. Okay, the top principal components. So yeah, the top singular vectors are basically going to be, you know, dominated by these rather heavy things. Okay, and this actually only gets worse when the true matrix is no longer uniform. Say there is actually some heavy rows and columns. This is exacerbated. And if you think about this, what's wrong with the naive approach? So what's the best rank 1 approximation doing? It's saying, find me a direction that maximizes the variance of kind of what I see in this direction. We have this noisy sampled matrix. We're trying to maximize this thing, find the direction biggest variance across this noisy sampled thing. It's not that surprising that this direction will find the noise. Right? That intuitively. Right? Okay. Okay, even if you do kind of, like Laplacian scaling, you scale rows and columns by their weight, things don't kind of improve much. And so, one kind of intuition behind the algorithm is the following observation, which is, it dates back, maybe 30 years to sort of Friedman, Kahn, and Simoretti, which basically says the only thing wrong with this naive spectral approach is the heavy stuff. So if you kind of get rid of the heavy rows and columns, then everything is fine. Okay? So you can think about this as saying if you have like the sparse random graph, you throw away all of the heavy nodes, then the spectrum of your graph is actually what it should be. Okay, so again, so this says, say this is a true matrix, this is your observed things, we have some heavy rows. So we can just arbitrarily get rid of some of these entries, make them small, and then things will be okay. But some of the, this will only, okay, so sorry. So in all of this stuff, it's sort of assuming that all of the row and column marginals are basically the same. And if they're all the same, then these things basically say, take any heavy row and column from the empirical thing, throw it out or prune it down, and then the spectral thing is okay. In our setting, some of the rows and columns might be heavy, right? Some of the words might actually be more likely. So we don't just want to throw out the heavy things. Maybe all the structure we care about is contained in them. So, okay, so at like a super high level, the algorithm kind of works as follows. First, you partition, say the rows and columns, you partition the words according to their kind of empirical counts. So you have the kind of block of heavy words, the block of kind of medium words, the block of light words. And then within each of these blocks, the marginals will be roughly uniform. And so now one can, throw out the heavy and light things within each block separately, do this kind of truncated SVD on each block separately, and then kind of stitch back, the singular vectors from each of the subblocks into some consistent way. Okay, so maybe the surprising thing is that even though one partitions things into a super constant number of bins, we only lose like a constant factor in the sample complexity. Okay, if you got nothing else from this other than the fact that you have some sparse matrix, the only thing ruining your spectrum is the heavy nodes, that's a victory. Okay. Okay, I'll say one thing about the lower bound case maybe then. Actually, maybe not. Elias looks eager to talk. I don't know.
Can you say a little bit about this? So you promise that you are rank 2, and you want to distinguish if you are like either rank 1 or rank 2?
Yeah. So okay, sure. So what's the lower bound going to be? So I'm going to give you sequences drawn from either one of two things. So either I'm going to give you uniformly random independent draws from the uniform distribution over n things. So either I'm giving you samples of uniform over n. That's case 1. Or case 2, I've picked a random partition of these n things into two sets, into two halves. So set S1 and S2. And then there's going to be a 2 hidden state Markov model. So state 1, state 2, where the chance of going between them is, say, a quarter. And the chance of staying in a state is 3/4. And whenever you're in this state, you get a random sample from S1. And whenever you're in this state, you get a sample from S2. Okay? And your job is to distinguish which of these cases we're in. So these are quite different, right? The entropy rate of this guy is log n. The entropy rate of this guy is kind of like log of n over 2, sort of, right? If you know which state you're in, or if I told you this partition into S1 and S2, then you know which state we're in based on the sample you just saw. And the entropy of the next state is pretty close to log of n over 2. Okay? So the entropy rate of this and this are quite different. These are quite different things. But I claim that's hard to tell them apart, given order of n samples. So how would you tell them apart? Well,
so what's the distance between the two distributions?
Given how many, I mean, it's constant, right? Like if you know S1 and S2, then I give you an observation, you know which state we're in, and then you know the probability of the next thing coming from the other set is a quarter, versus it should be a half. No, so the observations, given that you just saw something from S1, the probability of seeing something else from S1 is big, namely 3/4. So you can think of right, something like this. Yeah?
How do you map exactly the rank to probability?
So look at this is a matrix of bigrams. So I give you a length n sequence, pick a random spot in it, look at the two observations next to each other, and it's drawn from this. Yeah. Okay, so then basically the question is, so I give you this sequence of examples from one of these two. Your job is to guess which one it is. So, I give you some sequence of examples. You can think of it as like drawing a graph. Right, this is the example you saw first, example you saw second, and so on. Maybe, you see the same element again, and so on. And the question is, do you want to convince me that, this looks like this guy or this guy? Right? And this guy, if I give you lots and lots of samples, this guy will have more small cycles than this guy, right? Okay? And basically, the lower bound follows by arguing, how do you convince me that we're in this case? So suppose actually we're in this case, but you want to convince me that we could have been in this case. How would you do that? Well, one way is you could say, oh, I'm going to tell you a set S1 and S2 that's consistent with what you've seen. And if you can do this and convince me that this is consistent, then you've won. How do you do that? Well, you make up some set S1 and S2, which corresponds to just coloring the observations with two colors. And if you can kind of color these things in two colors in such a way that, 3/4 of the edges are monochromatic, then that's a good way of convincing me that, yes, this is fine. Right? Why? Because, if we were in this setting, and you actually told me the true S1 and S2, what would we see? We would see like a random path where at each time step with probably 3/4, we see the same color again. Okay? And so basically, the lower bound follows by just arguing that actually, even if these paths have length order n, someone could still come and do this coloring even when you're in this case. And so this is kind of a super high level. This is kind of the idea behind the argument. Yeah, Elias.
So maybe an argument of the sort of the message of this last thing is that there is no benefit to test versus to learn.
Yes.
This is for epsilon constant. For a given epsilon, it's also quadratic. It's like omega of n over epsilon squared. How you work this out?
For testing or for?
For testing. For learning is clear.
Yeah.
For testing is also like the two problems, even as a function of epsilon, they are the same.
No. So basically, once you can somehow make sense of what's going on a little bit, it's very easy to really figure out what's going on.
Is for this example or
in general, say for these rank 2 things, for these community detection settings, and so on.
So there is some testing
Yes. So one way of thinking about both this low rank setting and community detection is like, once you have some idea of the structure of the matrix, like even if you have just some faint correlations, you kind of know which community each person's in, then you can very easily really refine your sense of what's going on. So in that sense, there is this like pretty crazy, you need like order n samples to distinguish this from uniform. But once you can distinguish this, you can really start refining everything in the setting. So in that, what? As a function of epsilon? Oh, yeah, I don't know. This distinguishing, yeah, it's a good question. But it's going to be better than epsilon squared. Anyway, so I think, yeah, let's end there. But thanks.